Hi. Cool, this works. So this started as a you should go learn Kotlin talk, but actually this is a you should go learn Haskell talk and then take everything you learn from Haskell and just bring it back to whatever language you're working in. And surprisingly, that's actually a fairly approachable thing to do if you're working in an environment where the building blocks are kind of given to you. So what we're going to be talking about today is what a functional programming application looks like using Kotlin, using Spring. We'll be talking about improving your controllers, making them a little bit safer. We'll be talking about manipulating data. We'll be talking about building maximally polymorphic services. And we'll talk about doing lawful and statistical tests. And then, if there's a little bit of time at the end, we'll talk about what the future of functional programming in Kotlin might look like. So the techniques that we're going to talk about today mostly revolve around using this library, Arrow. Arrow is a functional programming library framework, and it builds on this idea by a pair of people, Yallop and White. They delivered a paper years ago called Lightweight Higher-Kinded Polymorphism. And it's basically a way of encoding higher-kinded types in a language that doesn't have higher-kinded types. It's a very cool idea, and you'll see a little bit of a snapshot through it throughout the talk. I recommend reading the paper. It's a well-laid-out paper with practical examples. You can read the paper and then build the library yourself as long as you have a language that has generics. If you want a really more in-depth delivery of it, I gave a more in-depth talk of how it works last year at Lambda Jam. But so we'll start, we're going to build a shopping cart application because everyone builds shopping cart applications. And we'll be taking data, taking a cart that someone's built in a website, processing it, applying discounts, finding out if there's any stock errors, and then returning that to the front end. So we start with data. Really quickly in Kotlin, you have a couple of things that almost look like algebraic data types. They're not quite, but they're pretty close. So we have these enum classes, which basically build tags but don't have like constructed data. We have a way to build classes, ordinary classes. And we have this tag, a data class. And a data class gives you all of these methods for free. The most important one that it gives you for free is this copy method. Now, things in Kotlin are mostly immutable by default and are mostly immutably bound by default. So without a way to update data inside a class, you'd be pretty lost. Especially because a lot of the standard library that you would share from Java doesn't necessarily give you that freedom. So the copy method lets you lets you change data inside a class and return a new instance of that class. So not mutation inside the class, but a copy of that data. So these are all good defaults, and they give us a good way to do nice things. So if we want to combine two carts, we take cart A, we take cart B. We construct a cart by calling the copy method. We take the line items from cart A, we append the line items from cart B. Take the errors from cart A, we append the errors from cart B. It kind of looks like something we used to in functional languages, right? It kind of looks like a monoid. So if we were going to define a monoid in Kotlin, how would we do that? And so this is something where Arrow helps us out a lot. The way that you deal with type classes and higher kind of types in Kotlin using Arrow is, like I said, this defunctionalization trick. So we have, we have this interface functor. That's the stand-in for our type class. So a functor is generic in F. And you can see here this kind constructor here, the word kind, generic in F and A. Kind is a way to map some generic structure F to wrap some generic structure A. It's basically saying, if I was going to pass a value to a function where I was going to say a generic F wrapping a generic A, this is how I would do it. Because you can't do that in Kotlin. You can't have a function where the requirement on a variable is generic in the constructor. So the kind trick allows you basically to take something that is a higher kinded type, bring it back down into first order types. And so we define this type class by defining the interface functor. We define our list. We've called it list K because we don't want to clash with the existing list. We have this higher kind annotation. The preprocessor that runs as part of Kotlin will take that higher kind annotation and generate out the next 3 lines of code. It'll generate out a tag that lets you basically pass that tag in place where you'd want to say this is a partially applied constructor. So that would be like passing maybe, or like passing either, without saying necessarily either of a throwable and a string. We'd have a type alias to allow us to go back and forth between the kind and something that stands in for the kind. And we have a way to get in and out of this kind syntax, because obviously a kind FA can't have any behavior that's specific about F. So if we want to use any of the methods or behaviors on F, we have to come back out of the kind. And then if we wanted to find the instance of a type class, we use the @extension annotation. We define our interface as it implements the required type class interface. And so in this case here, we say that for a list, we're going to say that the functor implementation, which implements map, allows us to call the function that exists on lists called map, which already exists. And that's how we define our functor. And now we can use this anywhere that we want to say, this is a function, it takes a functor. We don't say that it takes lists, we don't say that it takes maps, we just get to use it as a type class. So if we're going to define our monoid, we basically define here our shopping cart monoid. We say that a shopping cart's empty state is 2 empty lists. We say that our shopping cart's combined state takes all of the line items and joins them, takes all of the errors and joins them. And then we have a monoid. And we can use this, we can see in the use monoid function, we don't know anything about carts. We don't know anything about structures. All we know is that F has some way of saying F is a monoid. F0 is some type of F. F1 is some type of F. And we can combine them as long as we can say that F is a monoid. And that's what that first parameter does. That first parameter is what's known as a witness. So it lets you basically prove to the compiler that all Fs inside the scope of this function have the behavior given to them by the monoid interface. So that's the mock for higher kinded types. If we wanted to do deep updates, normally in a language that is immutable, you end up having these really deep nested structures. So you can see here we have some class relationship. We have this really deep update from an employee all the way down to the street to update it. There's this nice thing called lens that you might be aware of from Haskell, but it's a way of writing these getters and setters effectively. So the Arrow library ships an @optics annotation, which auto-derives lenses for you from data classes. So you have these data classes, you have these relationships, you tag them with @optics when you write the data class, and you get, for free, these lenses that allow you to do composed updates down through whatever the depth of your chain of data is, and modify it and return a new instance of whatever your top level thing was with everything copied, everything cloned, nothing mutated in place. So this is really powerful if you have these large structures and you want to kind of run through your program with them. So we've seen how to do type classes, we've seen how to do lenses, we've seen some good techniques for dealing with data as itself. How do we deal with if we're working with a user who actually wants to make requests to our system? So here we have a perfectly normal Java controller. This is not what I'm going to talk about a lot. But we have annotations all over the place. We have no real types that enforce the different behaviors that we're seeing here. So we've got our request mapping that says get to this endpoint and do this thing, and it doesn't really give us very much to reason about. We actually have to know exactly what the annotation does to understand the code that is generated, to have any way of really understanding what is this system going to do at runtime. So by contrast, without doing anything other than what comes out of the box in Spring, the Kotlin version of a router is much more first-class values as part of the language. We have an ordinary function to build the router. We have a router DSL, which lets you say what the routes that you're going to be dealing with are. We say that we're going to post to this endpoint and that we're going to use this handler to deal with it. So we can reason about this much more straightforwardly. We can actually understand, well, I can see here are all the invocations. If data comes in from here, here's where it will flow through. And I don't have to think about what are the annotations that I'm using to give me this behavior. So the only annotations we have left are for Spring doing mapping of, or injecting components. So this is the dependency injection that Spring gives you, which we'll cover off a little bit later. So personally, I prefer the second version. I think that it's nicer to be able to reason about programs. The biggest thing for me is the types are fairly weak in the Java version. The types are a bit stronger in the Spring version, and they get stronger depending on the libraries you use. But the design overall of the Kotlin version is a more approachable, more understandable design from my perspective. So if we talk about a handler, right? So we saw before we have this shopping cart handler. You give it a server request and you do something with it. One of the major advantages of Spring 5 for functional programming in Kotlin is they actually give you a quasi-monadic API for dealing with requests. They introduce a reactive extension like library called Project Reactor. which gives you these stream interfaces, one called mono, one called flux. We'll deal with mono exclusively in this talk. Mono is very similar to JavaScript promises. It encodes a value that is understood to be asynchronous in some nature. So it basically encodes a computation that will result in a value at some point, but without necessarily performing any of the steps at the time that you indicate them. You deal with it the way that you would deal with a functor or an applicative or a monad. You say, I have this thing that represents a computation. I want to then perform this action on the result, and then perform this action on the result, and then perform this action on the result. And then at some point you interpret it. At some point you pass it to a subscriber or to anything like that. And you can hop threads, you can give it instructions on what kind of elasticity to perform the operations on. It's a very powerful API. But there's one thing that really bugs me about it, and it's that it doesn't encode anything about errors. So you have nothing giving you first-class support for dealing with errors. There's a do on error callback, but that doesn't actually tell you what the error type will be. It doesn't help you enforce that we're going to handle these things, and this is what the standards that we handle are. So how can we improve that? What can we do to bring more types up into that? Well, again, we're using Arrow, so we have a lot of very nice, powerful tools. And the one that we can use here is the either transformer. So because we're in a good position to say any computation that is asynchronous but also returns something that might throw or might not, we're in a good position to say, well, that's going to return a mono of an either, where the left branch of the either is a throwable and the right branch of the either is the result that we're looking for. But that also means that anytime we want to interpret that computation, we have to take it out of the mono, take it out of the either, do something with the value, put it back in the either, put it back in the mono, continue the next function. And that gets kind of frustrating over time. So we have this either transformer, and that'll let us basically say, here is a way to unwrap this computation to get the value out of it, and to give you the way to transform it, and then to put it back into the computation that you're expecting. So there's a lot of syntax that you have to write in Kotlin because it's obviously not designed out of the box to give you this the way that Haskell is. But effectively, we can say the thing that we're working with is an either that has a mono, that has an asynchronous nature to it, that deals with a throwable or deals with a shopping cart. And it gives us an environment in which we can execute things that are safe to execute in that environment. So the binding function there, where we execute .binding, gives us something that's kind of like do notation. So if we execute anything that returns in a mono, we can call .bind at the end of it, and it will unwrap it and assign it to the variable, in the same way that the left arrow in Haskell do notation evaluates and assigns effectively. It's basically, instead of us having to do .flatmap, .flatmap, .flatmap all the way through. The nice thing here is that anything that returns a left, anything that fails at any point in the computation we have, will short circuit any of the following lines. So we don't have to handle errors in place, we don't need try catch, we don't have to think about what if something, how, anything like that. But we know that we have to handle them. So as developers, we know that we're being safe and saying, here's how we're going to handle the error, here's what we're going to do with it. And then we can write a function, which we have there, handle, and we say that handle is an extension to an either transformer. And for any either transformer of this type, we're going to extend it with this function to be available. And if you call handle, you just recover from the error and give back a server response that says something went wrong. So you can actually design your system in such a way that you can deal with these errors with an abstraction and not have to worry about, did I try catch that one, did I forget to do it? The type system has your back. It helps you understand these are the places where you might have these problems. So now that we have some data, we're starting to think about, well, how do we actually process it? What do we do with it? So we've seen how we can mutate or how we can deal with changing data. We've seen how we can construct type classes. And we've seen how we can improve our controllers to give us a semblance of safety. So now we're going to deal with the service layer, actually changing things. So again, the standard Spring approach. We want to use dependency injection to give behavior to all of our different things. We don't want to have to do the environment management ourselves. We want to just be able to send things through and not worry about how they got there. And we can see this is okay, but there are some really big drawbacks to this approach. The first is it's very verbose and it leads to a lot of boilerplate work. The second is, again, you have all these annotations over the place, which means you can't really understand where things are coming from. There's no easy way to click on the service annotation and see where this thing is defined. Threading environments is really difficult. and you end up with all these little trade-offs that make it hard to understand what's going on. The biggest one, though, is testing. So Spring DI, to its credit, basically insists that coherence is held within the system. So you can only have one instance of a thing that you want to inject into other areas. You can only have one bean, they call it, of a certain type in the system, which is fine, except you think about it, and at compile time, you want a different thing than you want at test time. And because we don't have higher kinded types, you only have effectively a monomorphic type for a computation you want to perform. So our shopping cart handler can only have one implementation. We can't say, you know, shopping cart handler of ID, shopping cart handler of list, and give us different ways to inject different behaviors. So the way Spring gets around that is another annotation. We have the profiles annotation, and we say we're running this in a test environment, use this bean. We're running this in a production environment, use this bean. But again, we end up in this world of where am I getting this thing from? How do I know what it is? How do I know what behavior it has? And the end result for a lot of projects is they just mock. So we have runtime mutation of behavior, and now that's a whole other world. That's another big risk to your project of, did I mock this accurately? Does it obey the interface? Does it, you know? So how can we avoid that? And the key word from my perspective is environment. We're talking about how do we thread an environment between slides. We're saying, between callers, sorry, thinking about the speech. How can we do that without this dependency injection machinery? How can we do that without annotations and without runtime failures and all of that kind of stuff? So the way that we can get to that result is, let's first think about the environment we want. So we know that there is some object that will give us the answer to all of these things. We're going to call that the environment. What behavior would we like the environment to have? Well, we know that it needs to have a service that lets us call out to the warehouse to say, are there any stock for these items? And we know that there's got to be something that lets us hit the database to say, what are the discounts available for this thing? So we can actually build type classes that will take something and say, do you have the behavior of, can I get a warehouse? Do you have the behavior of, can I get a warehouse? Can I get from the database? Can I do these things, right? So those are our has repository and has warehouse service type classes at the bottom there. And we can actually, by enforcing that requirement in a function, prove to the compiler that anything we pass in will have these behaviors available, and we get environment assumptions for free. Now we can define our env type. So we say that we have a higher kind, which gives us, again, all the machinery for the type classes. We can say we have an extension. So we say that our environment definitely obeys the has repositories interface, definitely obeys the has warehouse interface. And now when we use it, we can actually apply the environment and prove to the compiler that we have this. But even that's not quite enough, because we're still talking about passing the environment explicitly to every function. And we're threading it manually. Now that works fine, but it's very onerous. It's a lot of work to have to give a developer to remember, well, I take the environment here and I pass it there and I pass it all the way down my stack. So this is where the learn Haskell part of the talk becomes really important. There's this nice structure called a reader transformer, which I think in Kotlin is called a Kleisli type for one of the mathematicians who were involved in the type theory or in category theory for it. But so the reader transformer lets us basically say, in a monadic environment, in a monadic execution context, this is a way to get an environment and basically thread it through your computation. So this is kind of what that looks like now. We don't pass an environment explicitly. We have our calculate call. It's a function by itself. It doesn't need to be a class because we're not doing Spring dependency injection. We can just define a function as a first class thing. And we say, here are the behaviors of our function. You know, we have whatever the type that we're going to return the wrapper must have monad throw so that we can recover from errors. We say that the environment must have has repositories, must have has warehouses, and we pass in a cart. And we build up this computation without ever talking about where the actual environment is coming from. Because the computation doesn't care. As long as the computation knows I'll get an environment at some point, why should it have to know at every step of the way, well, I'm going to have to deal with this environment? And we can compose these things. One of the nice things with Kleislis is they compose really nicely. So we have a function that returns a Kleisli, and we just take the result of that and pipe it into the next function that returns a Kleisli. And we can build up these nice computations that deal with us dealing with this data and not worry about Are we in an asynchronous or a synchronous context? Not worry about, are we in mono, are we in ID, are we in list? Notice how that's not anywhere here. All we've said is the return type will have to implement monad throw. The environment will have to implement repositories and warehouses. And otherwise, write what you like. So this is what one of those functions look like. So we have our service called calculate. Calculate calls calculate discount. Calculate discount also doesn't take an environment. So when calculate calls calculate discount, it doesn't have to unwrap Kleisli, take the environment out, pass it in explicitly to a function. We actually just say, this computation returns a Kleisli, and because it does that, we know that when an environment is passed in, here's how it will be interpreted. So we're defining interpreters. And we basically say that we're going to take something that proves that the environment given to us by the Kleisli has this has repositories behavior. We're going to take something that has a cart. We're going to take a cart in. And here's the computation that we'll perform. But I'm not going to perform it until you give me an environment at some point. And we can update this stuff. We can run with it. We can have many of these things without ever actually performing the computation until we get to the point that the environment is important. When we pass the environment in, all of these generic values will be bound to the types given to us by the environment. So we can actually build up these computations in abstraction of what the environment is at the time that we run it. And I think that's a really nice idea for testing specifically. And so we'll talk about that with how we would start testing this kind of process. So we saw before that we have this calculate method, calculate, which needs a monad throw, needs has repositories, needs has warehouse services, and returns a Kleisli. And then for the calculate discount, we use the Kleisli function, essentially, or constructor, to say, here's the callback where env is of type kind fa, and I give you, you don't need more information than that, and you can deal with it however you want to deal with it. So how do we construct that environment such that we can actually pass it into this function? And that's the nice thing. Notice how we don't have annotation saying, I'm in a test profile now, so use this particular environment. We don't have mocking, so we're not saying, use the real production database code, but if it asks for a find all, give it back this list. We're actually just saying, here is the environment that we want to pass into the computation. The computation is the real production computation, but the computation doesn't really care about the environment. So here's the environment that I want you to execute in. And here we've said repositories are in mono K, external services are in mono K. That's the implementation we've chosen. It doesn't matter. We could have used ID and just had one value returned. We could have used list. Anything that has a monad throw would have fit fine into the environment that we're building. And it means that instead of worrying about mocking, we actually just construct an environment that is useful for the test that we're writing. And then we write our spec and we say that it runs the service. We construct an environment because env is just an ordinary class. It doesn't have any special behavior. It just takes these things as values. And we say, here's the input, and we construct a shopping cart, and here's the output, and we construct a shopping cart that we want to be transformed into. And then we calculate, and we call calculate with .run env. And we can see that's the first time and the only time in that entire structure where we actually pass the environment into that calculation. So this is really powerful. It's really nice. We can then have tests that are specific about asynchronous behavior, tests that are specific about non-asynchronous behavior. We can have tests that hit the database if we want to. We have all of this power to change the behavior of the things that don't really matter. We can reason algebraically about the computation that we're working on. So that's one nice aspect to testing. More functional ideas in testing are things like property-based testing. So property-based testing is really powerful for understanding behavior of your code. And this is one example of how you might set that up. Sorry. Kotlin has a library available to it called Kotlin test. And Kotlin test is a really, really great testing library. One of the reasons why I like it so much is it comes with property-based testing out of the box. And so you can say, here I've defined an immutable reverse method, because the reverse method in the Java standard library is not immutable. And we've said that we're going to take a list, we'll fold it, and then that will reverse it. So we use fold left, and we reconstruct the list, and that reverses it. And then we write a spec that says, for all, which is the way that we get into this property-based world, generate me out as many lists as you can think of varying different behaviors, and then assert that if I reverse a list and then reverse it again, that it's the same as the first list that I gave you. So The way that for all works by default, it gets 1,000 generations. You can give it any number. You can give it a run through of what you need. You can give it generators, and you can kind of run through with what you're getting out of that. But you can actually write your own generators. So if we wanted to test our shopping cart, we can say, here's a shopping cart. Here's how I generate line items. Here's how I generate all this stuff. Here's my sequences. When I call for all, this is what you should use to actually generate out me a shopping cart. Which is really useful because earlier we said that shopping cart was a monoid, but a monoid is more than just an empty and a combine. There are laws that have to be obeyed. Now, Arrow gives you a way to test these laws. So when you write a new instance of a type class, you can actually say, here is how it implements the type class. Here's how it actually runs. So obeys the monoid laws. We say monoid.laws. We give it the monoid that we want to test. We give it the generator for it, and we give it a way to say, are these things equal? And it tests it for you and tells you whether or not you actually obeyed the laws. So to close out, these are all really powerful techniques. These are all really nice things. But where do we actually go from here? What is the future of functional programming in Kotlin going to look like? So we have, this is one of the proposals by the creators of the Arrow library to the Kotlin standard, to the Kotlin compiler. And it is by far, by 6 times, the most popular proposal at the moment of any proposal ever to the Kotlin compiler. You can see it's very, very popular. And effectively, this is to give us compile time extension interfaces. So I'll skip this and just talk about the slide that we had before. We had this calculate slide before, but we had to explicitly pass in monad throw, has repositories, all these type class behaviors. But with the new calculate method, we can actually say, as an extension of the behavior that we had, here is what I want you to do. And at compile time, it will go and do a lookup of all the different interfaces that you've said you implement, and it will give them to you. So it's actually very close to type classes in general. And the way that that works involves a whole bunch of machinery on the compiler side, and a whole bunch of algorithms on how do I find the right instance and all that kind of stuff. But it's a really, really powerful addition to the language. And it empowers us to do the kind of functional code we like doing, but without a lot of the boilerplate that we would otherwise have to deal with. So closing out, I think the first thing is just because you're not working in Haskell doesn't mean that you have to be stuck in the pit of despair. You can take a lot of the ideas that are really great in these languages that we can learn from and bring them back with us to places where they may not be first-class citizens of the language, but they have powerful abstractions that we can learn from. Things that are cool are often really cool regardless of where you implement them. So domain abstractions are useful kind of independent of the domain that you're trying to apply them. You have to pick the right abstraction and the right place to use them, but you can get a lot of power and a lot of value out of it. And finally, one of the nice things about working in software, and especially in the functional community, is that we can see far by standing on the shoulders of giants. There's a lot of work that takes place in improving the developer experience, in improving the tools that we have, and just generally giving us a better environment to work in. And just because some of that takes place in a language that we might not be working in doesn't mean that we shouldn't try and find a way to take advantage of it where we are. So go check out Arrow if you're working in Kotlin and you want to know more about this, come and talk to me or come and join in one of the chat rooms. And thank you very much for listening.